So this morning I thought I'd go through the beginning at least of this test review. So here we go. If you take a look at the first problem, you can see that it tells us the equilibrium constant is 265 for this reaction. Then it says what is the equilibrium concentration if those of H2 and S2 are 0.002 and 0.001. Since it says these are equilibrium concentrations, then this is not an ICE problem. This is a simple problem where we just need to set up the formula and then put in the numbers and solve for X. So let's go ahead and do that. So Kc is equal to the concentration of the H2S squared divided by the hydrogen squared times the S2. All right. We know that the concentration of the H2 and the S2 are 0.002 and 0.001. We'll go ahead and put those in. 0.002, and that'll be squared, and then 0.001. We know that the H2S, now we don't know what it is because we're looking for the H2S. We know that Kc is 265. The H2S is going to be called X then. We don't know what it is, so we just solve for it. It is squared because of this 2. All right, now this is a basic algebra problem. We need to solve for X. To do that, we need to clear the denominator. So we multiply both sides by everything that's down here. They'll cancel on this side, so we'll multiply by 0.002 squared and 0.001. On this side, we'll multiply by 0.002 squared and 0.001. So let's go ahead and do that. I'll do it on the side here on the calculator. 0.002 times 0.002, because it's squared, times 0.001 times 265 equals. I get 1 times 10 to the negative, or 1.06 times 10 to the negative 6th. But that equals X squared. So we'll write that down. 1.06 times 10 to the negative 6th equals X squared. So we're going to take the square root of that. 0.001. So X would be equal to 0.001. And that the equilibrium constants are dimensionless, but the units of concentration are 0.001. So we always put our answers for concentrations in moles per liter. So that's the end of problem number 1. Problem number 2. With the same kind of logic, the difference is in this problem, these chemicals are placed in the container. So that we're actually just the PCl5 is placed in the container. So we say Kc is equal to the PCl3 multiplied by the Cl2 divided by the PCl5. I'm going to rewrite the equation down here, the chemical equation. So PCl5 decomposes into PCl3, phosphorus trichloride, and just chlorine gas. The difference again is that between this one and the previous problem is that the 0.3 moles is placed in a container. So we're going to have 0.3 moles in a container. It's in a 1 liter container. You remember that you need to put it in molarity, but 0.3 divided by 1 is just 0.3. But you do have to divide. So that's 0.3 molar. We don't have any of this initially. So those are the initial containers. We know that some of the PCl5 will react, but we don't know how much of the PCl5 will react. So we just say it goes down by X amount. Since there are 1-to-1 ratios, then this will go up by X amount, and this will go up by X amount. If there was a 2 here, that would go up by 2x. So 0.3 minus x, x was what we will have at equilibrium. So again, we're thinking about initially how much it changes and what is the equilibrium concentration. All right, now we are ready to solve the problem, and it is a problem that's going to require the quadratic equation. So let's go ahead and plug in what we know. We know that the PCl3 at equilibrium will be x. We'll know that Cl2 is going to be x. And we know the PCl5 is 0.3 minus x. Now all that's equal to the equilibrium constant, which is 0.1. Now we need to do algebra, so we're going to multiply both sides. Remember how we clear out the denominator. So you've got to multiply both sides by 0.3 minus x. Cancel out over here. We're going to have x squared left on the right side. And then doing the math on the rest of the problem, 0.3 times 0.1 is equal to 0.03. So 0.3 times 0.1 equals 0.03. That's going to be minus 0.1x. So I'm multiplying this by 0.3 and this by x. So now we know that I'm going to add 0.1x to both sides and subtract 0.03 from both sides. So 0 on this side, because I'm going to take away 0.1x minus 0.1x. I'm going to add, or excuse me, I said that wrong. I'm going to add 0.1x, not take it away. All right, there we go. And I'm going to take away 0.03. So minus 0.03. All right, so I end up with 0 equals x squared, there's supposed to be an x there, plus 0.1x minus 0.03. Or I like to write it like this, x squared plus 0.1x minus 0.03 equals 0. So now you have your basic quadratic form. All right, so now we'll do the quadratic equation. We know that x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. The b term is 0.1, so we're going to have negative 0.1 plus or minus square root of 0.1 squared minus 4 times 1 times negative 0.03. You got to watch that negative 0.03. Because that changes the sign underneath the radical here. Okay, once again, the a term is 1, the b term is 0.1, the c term is negative 0.03. And all that's divided by 2a, which is 2. So I'm going to work out what is underneath. I'm going to go ahead and do everything in this area because it's easier to see the problem's solution when you do that. So it's negative 0.1 plus or minus. And I'm going to work out what is all that stuff underneath the radical. So it'll be 0.1 squared. 0.1 times 0.1. And then I'm going to add 4 times 0.03 because minus a minus is a plus. So plus 4 times 0.03. I'm skipping the 1 because 1's just 1. And I get 0.13. Then I'm going to take the square root of that. I get 0.36. So our answer underneath the radical is 0.36. And all that's divided by 2. See how much room I've got? Kind of running out of room. So I'm going to come over here to continue the problem. So now negative 0.1 minus 0.36 would be a silly answer because that would give us a negative number, and since the answer is going to equal x, x can't be a negative number because that would give us a negative concentration, and that'd just be silly. So we can't have a negative concentration. Therefore, we have to use the negative 0.1 plus 0.36. Then we're going to divide that by 2. So x equals 0.13. So that means up here, x is 0.13. The Cl2, the PCl3, then at equilibrium would be 0.13. The Cl2 is going to be 0.13. And then this is 0.3 minus 0.13, which would be 0.17. And those are the answers. So 0.17, 0.13, and 0.13 would be the equilibrium concentrations respectively of the PCl5 and the PCl3 and the Cl2. All right, there we go. That was problem number 2. Problem number 3. For the system given here, we know that we have 1, 3, and 0.4 placed in a 1 liter container. Once again, this problem is nice because it's in a 1 liter container. We need to know molarities, but it's easy because you just divide by 1. All right, is the system at equilibrium? Well, this is a simpler problem because to find out if it's equilibrium or not, you just set up the constant, Kc, is equal to the products, PBr5 concentration, divided by the reactant concentration, PBr3 and Br2. Remember, these brackets mean moles per liter. All right, so now we plug in the numbers we have. For the 1 mole of PBr3, I left off a 5 up here. That confused me momentarily. So this is supposed to be PBr5. All right, so now we plug in what we know. We know PBr3 is 1. We know the Br2 is 3. I'm getting that from up here, 1 divided by 1, 3 divided by 1, and then 0.4 divided by 1. So now I work it out, 0.4. Then I'm going to divide by 1 and divide by 3. So really 0.4 divided by 3 is 0.13. All right, then you compare this number to the actual constant. So this is called Q. Okay, Q is the reaction quotient. So the reaction quotient is 0.13. The constant is 0.25. Is 0.13 bigger or smaller than 0.25? Well, it's smaller. If it's smaller, in order to match the equilibrium constant of 0.25, it needs to get bigger. So in order to make it get bigger, the equilibrium process would need to shift to the right. In other words, we need to have a bigger amount of this and less of both of these, because if the numerator gets bigger and the denominator gets smaller, the ratio gets bigger. So we know that this will move to the right. I'm going to stop here and make a separate movie for the next section, but before we do that, I want to make sure that we know that this is not a system that's equilibrium. It will move to the right as it attains equilibrium. Down here, when we get to these movies, we're going to talk about left and right shifts, but the left and right shift is down here is for systems that are already at equilibrium and we're putting a stress on it. We're not doing any stressing here. We're just finding out if the system is at equilibrium or not. Okay. So Q equals 0.13 was smaller than the constant. So we needed the ratio to get bigger to match the constant. To get bigger, you've got to have more numerator and less denominator. So we know that this system will be moving to the right in order to attain equilibrium. All right, I'll stop there, do another one in a few minutes.